In this problem, we're computing a first approximation for the rotational kinetic energy of the Earth. So we're making a lot of simplifying assumptions here. We're asked to treat the Earth as an isolated, uniform, rotating, rigid sphere. And we can find a number for the rotational kinetic energy based on this crude approximation. But I do want to talk about at the end of the video how much this differs from the common values that you'll find on the internet and why the discrepancy makes sense. So first, just to get this rough approximation done, we're given the mean radius of the Earth as 6,371 kilometers. Keep in mind, we're going to have to convert that to meters so we get the proper SI units out of our calculation. Secondly, we're given the mass of the Earth as about 5.972 times 10 to the 24 kilograms. And third, we're given the period of rotation for the Earth as about 23.93 hours. Now, I do want to point out here, that's actually the sidereal period. That's the amount of time it takes the Earth to make one complete rotation with respect to the distant stars. So if you don't want to think about the details here, just remember the real period of rotation is slightly less than 24 hours. If you like thinking about the details, the discrepancy here is caused by the fact that the Earth has to go through a little more than one rotation to get the sun to the same point in the sky. So our usual number of 24 hours is actually including a tiny bit more than one rotation. So we could say that 24 hours is the length of the solar day, while the more accurate period for the purposes of doing physics is the sidereal period of 23.93, just slightly less than the 24. So as we get into the calculation, I think we'll just go ahead and split it up, and we need to compute the moment of inertia of the Earth, and we need to get our angular velocity written in radians per second. Then we're going to use the rotational kinetic energy formula, 1/2 I omega squared. So let's go ahead and start with our moment of inertia. And recall, the moment of inertia for a solid sphere is 2/5 mr squared. Again, that's based on the assumption that we have uniform density in the sphere and that the Earth is perfectly spherical. So note, as I'm plugging in the radius here, I'm going to convert the 6,371 kilometers to meters. So that's 6.371 times 10 to the third kilometers, but when I change to meters, I have to tack on another 10 to the third. So I have 6.371 times 10 to the sixth meters, and I need to square that. And this gives us about 9.696 times 10 to the 37 kilogram meters squared. Now for our angular velocity, I want to express that in radians per second. So I'm going to start with the fact that I have one rotation for every 23.93 hours. Then we can start doing unit conversions on this. So I can convert rotations to radians. One rotation is 2 pi radians. So this will give me radians in my numerator, 2 pi radians divided by one rotation. Then I need to get the hours converted to seconds. So 1 hour is 60 minutes and 1 minute is 60 seconds. So this is a nice opportunity to do some unit analysis in this problem. Note that all of our unwanted units are going to cancel here. The rotations cancel, the hours cancel, and the minutes cancel. And we're left with radians in the numerator, seconds in the denominator. That's exactly what we wanted. So this gives us an angular velocity of about 7.293 times 10 to the negative fifth radians per second. So finally, we plug into our rotational kinetic energy formula. This is analogous to the translational kinetic energy formula. Remember, that was 1/2 mv squared. But in rotational dynamics, that moment of inertia I is playing the role of mass, while our angular velocity omega plays the role of velocity. So we sub in our number for the moment of inertia and for the angular velocity written in radians per second. And this gives us about 2.58 times 10 to the 29th joules. So when I write a problem like this, I generally like to go on the internet and find out what other people are saying. And when I went to the Wikipedia article, it states a substantially smaller rotational kinetic energy. This is actually about 17% smaller than the number that we got. And when we look for a reason why this happened, the reason why is because the moment of inertia is much smaller than the moment of inertia that we got. Note that our angular velocity over here came out about the same. So it's really the moment of inertia calculation that's to blame here. So to look a little deeper at what was going on, I clicked the link to the reference here, reference number 3 in the Wikipedia article on rotational kinetic energy. And reference number 3 was a page on wolfram.com. And on this page, it was mentioned that we're considering the Earth is actually an oblate spheroid instead of a perfect sphere, and two different sources gave answers that were very nearly the same for the moment of inertia of the Earth as about 8 times 10 to the 37 kilogram meters squared. Now, it doesn't make sense to say that this is because the model was an oblate spheroid. In other words, with the equator bulging out slightly compared to the poles. Because in an oblate spheroid, more mass is farther from the rotation axis and the moment of inertia should actually be more. So this result is still confusing, but we can see we have some consensus here among the experts. So next, I went to the references for the Wolfram article. And these are both textbooks that were published in the late 70s and early 80s. And as it turned out, these are both graduate level geophysics books. And this is the moment that it occurred to me our assumption of uniform density is actually what's to blame for the discrepancy in our calculations. A geophysicist is definitely going to consider the fact that the Earth has non-uniform density. In fact, the deep interior of the Earth is significantly more dense than the crust. And now this makes sense. We have more mass concentrated closer to the center, and that makes the moment of inertia smaller. Remember, in general, the more mass you have farther from the rotation axis, the greater the moment of inertia. So with Earth having a much higher density toward the center, we have more mass closer to the rotation axis and therefore a smaller moment of inertia. So if we go back all the way to the beginning of the problem, it makes a lot of sense to make a coarse first approximation of a calculation like this. But we can understand based on physical reasoning why this first approximation should actually be an overestimate. In this case, it was actually an overestimate by about 17%, but at least we get the right order of magnitude out of the approximation. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.